Hello, everyone, and welcome to our monthly lecture. As a reminder, this lecture is being recorded and will be available on our YouTube channel in a few days. My name is Valérie Laflèche, and I'm pleased to introduce today's speaker, Christopher Davis. Christopher will be showing us functionalities in Geoscience ANALYST for pre-processing and visualization of DCIP 2D and 3D data. If you have any questions during the presentation, feel free to type them in the Q&A or raise your hand, but please be aware that Christopher may wait until the end of his presentation to answer. Christopher, the floor is yours.
Great, thank you very much. Yes, today I will be looking at DCIP data, and we'll start with ASCII data. So let me just minimize that back. So we have had in the past, ANALYST has always been able to import UBC data, at least for the last year or so, in 3D. Today, I will be starting off with ASCII. So here we're dealing with comma delimited files, because these are often files that we have just lying around or from other software. To import a file, you go to ASCII importers and DCIP data. And in here, we will find our file, L1, and we'll bring it in. And here we have an import DC data. We have the name of the object we want. And you can see down in the data preview, it's not very good because we haven't told it everything it needs. So here we have actually two comment lines. So we have these ignore lines now in all of our ASCII importers. And as soon as I go to 2, we're getting closer. But now we have a bunch of commas up above. So we need to change from white space to comma. And that's so much better. So first, now we have the data preview and it looks pretty good. And so now what we need to do is we need to fill out our transmitter and our receiver or MN values. So for our transmitter 1, we have AX, AY. We do not have to give it a Z. We have a transmitter 2 in this case. It is a pole-dipole, as we'll see, but I'll fill it in anyway as an example. We do not have to have a second transmitter. So really, at the minimum, we would need an X and a Y for one transmitter and one receiver, which would give us the pole-pole. So I fill these out. So now I have no Z values, X and Y for M and N, and A and B. There we go. Aha. And you can see here that it now has come in as a DCIP object. So each DC object has a potential. So it has the pseudo section with a P for potential and 1 for current. And these things are linked, as you'll see in the metadata. And this is pretty nice because if I move one out, it'll move the other out. So you no longer have to multi-select to move them. I'll go ahead and bring in 2 more lines. So I'll go to line 2. This one's for time, a bit nicer. So I have T1. And so it recognizes I do not have T2 because it's just a pole, and then it recognizes the RX 1 and 2 as well automatically. And I'll bring in my third DCIP data set here, L3. And again, we're good to go. Great, so now I have 3 lines of data. What I can do is, if I bring these out and delete this ASCII, if I hold down Control and multi-select, this is actually a general feature, but if you multi-select on different objects but are the same type, you can see over here in the visual parameters, I now have 3 objects. So if I wanted to increase the node size, I could. I could also, show segments or change the symbol. I could also change the transparency as well, or set it all the same color. in this case, the other thing we've done is we have added the AB cell ID to both the potentials and the currents. So now you can see where the current is. And so we start at from 1 to n, which in this case is 21. But if I select them and go to the colors, if I had a description, I could import it that way, or I could just simply change the name of one of the AB pairs from say 18 to important with a different color if I really chose to do that. And so now when I'm in my potential pairs, if I come down to the here, you can see that I have important and AB pair 17. So these now describe something that we might want. The other thing I'll do is I'll turn on resistivity. And now that I have resistivity, I'll just go ahead and bring it over to this data colors and set it here to a log scale. So I now have a log scale. And with my visualization, I can look for a specific style or specific AB pair. I can also look at all the data that are upline. So here we see that line 1 has upline data, and line 1, 2, and 3 have downline data. So those are just simply MN pairs that are downline of the AB pair. And you can see how the data changes, particularly in line 1 here, when I go back and forth. And then all will fill in the gaps, and we'll show you whatever's first. And again, now that I have the potentials, if I view only this guy, if I uncheck, I've now checked off all of it. But if I search for that all important AB pair, I now have the AB pair, which in this case, again, is a dipole, is just a pole at A. So B is equal to A. But it will, as I click down, I not only see where I am in the data table, but I see my MN. And in starting in 3.4, we now will also see AB if it's a dipole-dipole. So you'll see both MN and AB connections. And now I'm also looking as a function of apparent resistivity. So far, everything I've shown you is in the viewer version, so the free version of Geoscience Analyst. Now I'm going to switch a little bit to some pro version functionality. So I have these 3 lines, which are great, but really at the end of the day, if I want to do, say, a 3D inversion, I'm going to want these all in one object. Now I can right-click and choose all my objects and go to Create and DC IP data from selection. And maybe I'll call this all lines. And while we're doing that, I'm going to view only all lines. I'll also create a group, call it old lines. And I'll just grab a couple and move it in there just to hide them a little bit. Now, when I've merged these groups, all of the AB cell IDs are now changed to the original line number or the original name of the object and the actual name of the AB pair. So here we have the line 1 important, even though it might be AB pair 37 now. And then we also have, again, the resistivity, which we can see here. So let me just increase the points. So now if I look out, this is much closer to an actual pseudo section. And again, we have all of our AB pairs. We have all the upline and downline, and you can see how they've now changed direction, especially in the first one. So I brought in lines again, but in this case, they're actually all in local coordinates. So if I put it in map view here, you can see they're all north. So what we can do is right click on the potentials, and we now have apply coordinate lookup table. So we'll go ahead and find our lookup table. Let's see, where is it? It's right there. And then what this lookup table asks us is, where are the current X and Y's and where are the new X and Y's? So we'll go from our local XY to our global XY. And the way we do this is we actually look at all the data locations. If they match up directly, we just simply shift them where they should be. If we have data locations that do not match up, we will use each coordinate system to try to infer where the new coordinate should be. So we don't go from line to line or the line ends. We actually do the whole thing as 3D. So in this regard, if I'm going from a bunch of local to global coordinates, it makes it a little easier if I don't have all of my data to at least have them spaced out approximately where they should be. So now, if I select down here, you can see my pick is now at 10,000 and 12,000. So we are farther away than we were when we were just at 0, 0, 0 for our origin. We've also now moved these lines that were north-south to east-west. I'll also say, in this case, we have all of our data. If we didn't have data and we actually had to interpolate it, we would actually have gotten another Boolean data property that has interpolation, and it would actually show us which of the data had sections, which of the nodes had to actually be interpolated. So now that we have this, and we're good to go here, you can see we have the lookup table XY and the copy of XY and where we are now. So we can always go back by simply scripting. We could also save this using this button right here to export the table to a CSV. This actually would now also qualify as a lookup table. When we brought in, we have resistivity. So it's apparent resistivity. To invert, we'll need normalized voltage. So what we'll do is we'll right click on the potentials and calculate apparent resistivity or voltage. So if we had a voltage, we could simply say, hey, we want to calculate apparent resistivity, and it will ask us for our voltage and our current if applicable. And in this case, we're going to ask for the voltage from the apparent resistivity. And this will be normalized voltage. Which looks like this. So it's obviously a little similar. And so now we have normalized voltage. And we're on our way to being able to start an inversion. We do have some DEMs here as a data mine file. So I'll import that triangular wave, the triangulation here. So here is our DEM that we have. It's pretty flat. You can see the min and the max go from 300 to 500 or 400 to 500. So it's not much. But our data here is sitting way down here at 0. So if we were to right click, we could drape on our topography. So now it's showing us where the data were actually acquired. And you can see someone had to walk up and over the hill. And our pseudo section has also updated like that. Now we don't have to actually know where our Z values are. We let the inversion, whether or not it's SIMPEG, UBC, 3D or 2D, deal with the Z values. If we had downhole data, we would not have wanted to drape that because we would want to keep the data where it actually was. A lot of times we have outliers in the data. So for this next part, I'll just show you how to create masking property for the data. So let's say that we don't want to see, or we don't want to capture the bottom part of this data. One way to do it is if I select Shift, I can select the data. Got to be on M and pairs to select it. There we go, and then it'll highlight. So again, if you're trying to select something, remember where the tabs are, and that's what you're going to select. So here I have a selection. If I right click and create masking property as a pro feature, in this case, I'm actually going to pick the non-selected indices. So everything that's not selected, I'm going to call it good and hit apply. And now I have a masking property that's true or false. We can say disregard, or we can call this keep. We don't have to keep it true or false if it makes it easier. So if we go back to our voltage and I select a point like that, I can see in here that I would want to disregard it. To be able to actually disregard it, what I'll do is I'll right click on the voltage and I'll apply the masking property, and I'll call this voltage good. So now we can see that the voltage that we have here is our quote unquote voltage good. And if I select something down here and say, well, this point I really don't want, I can always go to this button here to allow editing. And I could either remove this completely, or if I hadn't applied the masking yet, I could actually say, okay, I'm going to change this to disregard. And then if I applied that masking again, it would do that. So in this case, I haven't actually touched the original data, so I still have it, so I could always go back. Last thing we would need to do for the data to be ready is to assign uncertainties. And in this case, we'll create a GIF tools group, and we'll slide our data in. And in terms of GIF tools, we need to tell it it's DC data. And now we can go to assign uncertainties. We could also, as soon as we assign uncertainties, we could export it in UBC format. So if we were simply trying to bring in data from ASCII to UBC, we could do it that way quite simply. So we're going to choose our voltage good, give it a 5% floor. One way to look at this is to go to your voltage as you're looking at it. This doesn't help much. So what I'm going to do is select the lin log, and now that gives me the log distribution for the histogram. I also have the minimum, which is really hard to see because there's quite a bit. So I'm going to increase the display and use scientific. So now I can see, okay, that's 6e to the minus 6. So for that reason, I'll use something like 1e to the minus 5 and 5%, and I'll just call it uncertain. And now I have our uncertainties here. And then I would just go and add the metadata to voltage good and uncert. And this is where for UBC, we ask you if the object contains borehole data, because if it doesn't contain borehole data, regardless of where you have draped it, we will not export the Z locations. So we'll only export the Z locations if you've actually clicked that. And that's just to make sure that the UBC program itself will recognize there's no Z, and it will put it where it should. So you don't have data that's hovering just a couple meters into the air, which will just ruin your inversion. And so now we're ready. So if I wanted to invert this with UBC, I could go to inversion and select a DC IM 3D or a DC IP 2D inversion. If I did 3D, I would use my utilities and the blockModel designer to create a block model and set that up. If I have data that's already in 3D, I can always go to import UBC data, and I can just simply ask for observations files. If it's suffixed as a .dc in terms of this guy or a .ip, you can just drag and drop it, and it will import it. As you can see here, it'll import it as a UBC data file in 3D. And then lastly, this is a new feature in 3.4 that right now we have in Pro Geophysics because it was a bit late to the game. However, it should be available in 4.0 as just a simple import. And that's the DCIP 2D data or mesh and model files. And I'll just show the mesh and model files to finish up. So I select the mesh and the model files. And in this case, I have a DC inv2d.con, and I hit OK. And now it's in 2D, so it's asking me to set the spatial information. I have a line identifier. That's if I wanted to then combine them later on. I'd at least have that. I can put the direction, set the Y value, or give it a coordinate lookup on import. And in this case, I have a line lookup. So there's my lookup table. So my local to global. And if I look at my data colors, I can see where it is. And if I add my DEM, I must use a different DEM. But anyway, so now we have our, there we go. So now we have our 2D inversion on our lines. And lastly, if I wanted to visualize just this line, I would select this line here, and I could visualize line 2, just like that. And with that, I'll leave it for questions.
All right, thank you, Christopher. And thank you to everyone who joined us today. We already have 2 questions in the Q&A. If anybody else has other questions, please do type them in. And if you think of questions after the meeting, please don't hesitate to email us at support@mirageoscience.com. So while Christopher has a minute to read your questions, I'll take the opportunity to invite you to join us next month when Philippe Drouin will show us how to create a 3D geological starting model from geological maps and structural measurements in Geoscience Analyst Pro.
Okay, so I have 2 questions here. It is a good question. Both of these are good questions. I'm not actually sure I know the answer to, and one I knew was coming even, which is bad. So there was a question on saving the template on an import CSV. I believe that's on the automatic data loading settings. And I believe originally that was written for ASCII file for drill hole data, but we can apply it to all. So I'm not quite sure. So what I'll do is we'll figure that out. I'll figure out exactly how to use this, because shockingly, I actually don't know how to use this to be able to bring in data. So when I find that out, Benoit, I'll actually send you an email. And then the other question was if we had a platform to program data acquisition for ERT. So I will say that we do have a survey designer. And we have a DCIP survey designer. So if you had your area of interest, you could say draw a line of data that might look like this. And then these data are pretty long. So what maybe I need is like 100-meter station spacing. And you can see now it's changed a bit. And then I have a dipole, or maybe I want a dipole pole, or I could go down to, n equals 18. I could do upline and downline. It has a whole host of things you can do. And then if I create that survey, I now have a survey that I could export as UBC format in terms of locations, or use for UBC forward modeling. And there it is right there. And that comes with the AB cell ID and the pseudo location.
Thank you, Chris. We have a third question.
Yes, so it was about bringing in the crooked IP lines and local coordinates and import them into a UTM file and getting a 3D view of the pseudo section. So I basically, if you had ASCII file formats, that's exactly what I just did. And if you had 2D data that was in UBC format, just like I had brought in the DCIP 2D line here, if you had a UTM lookup table, which I did, it just happened to be flat, but if it actually curved 90 degrees, it would also curve this as well 90 degrees. And if you have Pro, you can always apply a lookup table after the fact if you bring it in. And that is for both DCIP and the draped model.
All right. So there are no other questions. So thank you very much, everyone, for joining us. And thank you, Christopher. And see you, everybody, next month. Thank you.